So for this lesson, we are going to begin continuing on learning some more about electricity and how it moves through a circuit. We are also going to begin getting into a little bit of wiring diagrams so you can start understanding how wiring diagrams are constructed and how to start to read them and start understanding how things are constructed throughout the circuit. So the first thing that we have to understand is, what is a circuit? Well, an electrical circuit is a full path for electricity to flow. In order for us to have a full path for the electricity to flow, we got to have at least 4 parts to it. We need to have a power source. We need to have a switch. We need to have a path, and we need to have a load. If we do not have one of those 4 parts, we technically do not have a complete path for electricity to flow. Now, your power source, that can be really a lot of things. It could be a battery, just like in a flashlight. It could be a transformer, which we are going to cover a lot later in further lessons on how we use a transformer to be used as an actual power source. A wall electrical outlet like we have in our houses, our power lines that are on our telephone poles and power lines outside, our breaker panel, and obviously our power plant where our power is being generated. Your path is a wire. It's a circuit board. It could be a piece of a grounding strap. Okay, a path must have a very low resistance, and this allows the electrons to move freely and without heat. A path with a high resistance is going to heat up. So when we look at electrical wiring in HVAC equipment, we want to look at the wires. We want to look at the insulation around those wires. Are they heating up? Did they melt? Do they have any signs of maybe cracking, missing, sort of any like deterioration type stuff? Because if that is, there's a chance that those wires are heating up too much and we have a problem with the electrical flow going through those wires, because maybe the wire just has too much resistance. It could be the wrong size. A switch is basically a valve or a gate that stops the flow of electrons. We got to have something in the electrical circuit that's going to start and stop the electrical flow. Does this mean that it's an open in a circuit? Yep, it is. Okay, when we turn a switch off, that switch is now in the open position, which means that the electricity is no longer flowing, which means the light shouldn't be on. Okay, now we add 2 more terms. Okay, an open is a gap in the path of a circuit that stops the flow of electrons. Closed is a path that is complete, that allows the flow of electrons. So when we turn a switch on and the light turns on, we have closed that switch. We are allowing the electricity to flow and have a complete path. A load is the portion of an electrical circuit that actually does the work. Okay, now this is obviously, it could be a light bulb. Okay, the work that is created is heat and light. A motor, the work is turning the shaft. Okay, a heat strip, that works to put off heat. Okay, think about like a toaster. When we flip our switch down and we're toasting our bread, we have the electric heat strips that are on the side. We're using the electricity to heat up those little electric heat strips so that we can toast our bread. A coil That works by creating a magnetic field, and when we use that in HVAC, we use that magnetic field to open and close contacts on either a relay or a contactor or some sort of electrical control device. Now, the pictures of a circuit is called a schematic diagram. These diagrams are composed of symbols that represent each part of the circuit. These symbols are called schematic symbols. So here is a very basic, simple electrical diagram. Again, remember, we have to have our source, path, switch, and a load in order for the electrical circuit to work. So our power source is going to be designated by using L1 and neutral to signify some sort of lettering to signify that these wires are our power source. So this wire right here is my power source. This wire right here is my neutral. We have our switch. We have our path, which is a wire. Here is our load. Right now, this switch is in the open position. When I think about switches, I like to think of them like a drawbridge. When the drawbridge is in the open position, the traffic cannot make its way down the road. But once I close this drawbridge and I make contact, that electricity can now flow down the road and into my load, where I can now do my work. Okay, schematic switches, there's a lot of different switches that are out there, but here are a couple simple ones that we have. We have your single pole, single throw switch, which is pretty much your standard light switch that you have on a wall. You have a single pole double throw switch, which is found on some HVAC equipment if we are using it to control maybe two different types of devices. A relay is an example of a single pole double throw switch, which we will obviously cover in a little bit later lesson. But when we break down our switches, they're broken down into our poles and our throws. Our pole is the power that is supplied to our switch. The throws is which direction that electricity is going to flow. So in this case, with this switch being in this position, electricity will flow through the switch and out through this wire. If this switch was to happen to come down, electricity will just simply flow through this wire and not that wire. So sources on a schematic. This is a breakdown of an HVAC schematic where we will locate our sources, our paths, our switches, and our loads. So our power sources on our schematics can be labeled either L1 and neutral, which is going to usually signify that we are working with 120 volts, L1 and N. L1 and L2 is usually going to designate that we are working with either 208 or 230 volts of electricity. Or we may see L1, L2, and L3 is when we are working with three-phase, which is normally found on a lot of your commercial type applications. So here, up here is our power source. Notice we have L1, L2. It's telling us we have line voltage, which is 208, 230, single phase, 60 hertz. So we have our power sources right here. Our wires, or our paths, is signified by our lines. So L1, we have power coming down through our lines. Okay, so each one of these lines will represent a wire. Next, we have our switches. Okay, our switch is represented right here. Okay, this is a normally open contact, which can be simply signified as a normally open switch. We have a switch down here. We have switches over here. Okay, and then we have our loads. Our loads are right here. These are all of our pieces of equipment that are actually going to use the electricity to do something. So here's the load, that's a load, that's a load. This guy here is a load. I just didn't put a wire to it or a line to it. Here's a transformer. This is a step-down transformer right here. That's also a load and a source, which we will cover in a little while. But then you have, of course, you have a couple of loads down here. Here are your coils, which are going to operate your contacts up here. And we will cover that in a little while. So loads on a schematic are shown by either an actual schematic symbol for that load or by a circle with a letter or some sort of key, some sort of designation that's going to tell you what it is. Loads are the portion of the circuit that actually does the work. So here is a breakdown of what we're talking about. So here we are, L1 in neutral. That's signifying our power source. Here is our switch. Our lines, again, are representing our paths. Here are our contacts, which are also just simply nothing more than switches. And our loads. And notice that our loads are just kind of just designated with letters. Okay, so fan, compressor, maybe blower, whatever it would be that we are dealing with a type of diagram. When it comes to wire colors, see, in HVAC we like to try to keep things somewhat simple. So when we're working with electricity, wires are going to usually be color-coded in some sort of way for ease of identification. When we are looking at wiring diagrams and wiring, our wires are going to be usually color-coded with our black wire signifying our line voltage. White is going to be our line voltage neutrals. Red wire is usually going to be our control voltage, power source. And usually blue is going to be our control voltage common, or sometimes we call it a neutral. But the thing is depending on who wired these units, usually the control voltage common sometimes can be a different color. But you just kind of have to kind of look at your wiring diagram and just kind of figure it out, see which one is what. But for simplicity, usually we use black for all of our power wires, white for all of our neutrals. Red is going to be our 24-volt control voltage power source. And usually blue is going to be our 24-volt common.